Okay, so the next little section isn't a big deal. Okay, it is an important concept in the term in the field of collisions, but we're not going to get too deep into it. Essentially, momentum and collisions in two dimensions. We've already said that momentum is always conserved. Momentum is also always conserved independently in each dimension. Okay, so what does that mean? It means that PIX has to equal PFX. PIY has to equal PFY. PIZ has to equal PFZ. Okay, so even though we can have a very complex collision, playing pool is a huge example of this. Even though we can have a really complex collision, momentum is conserved independently in each dimension. So here's on the picture on the bottom, thinking about pool, it's perfect. When you first, the first thing you do in pool is you have to break, right? So the person sets up the cue ball and they hit the cue ball into the big pod, I don't, whatever you want to call it, of the other balls, and they're set up in a triangle. And all of the initial momentum comes from that initial hit of the stick when you're breaking. Okay, so balls are going to go to the right, balls are going to go to the left, balls are going to go backwards, balls are going to go up and to the left, up and to the right. And the point is that when the motion of these, after the collision, when the motion of all of the balls are added together, the net momentum in each dimension is 0. So that means if this ball right here goes to the left with some velocity, this ball right here goes, or a ball, this is just an example, a ball goes to the right with that exact same velocity. Or I should say rather that the sum of all the balls would equal 0 to the left and to the right if all the momentum came head on. So in the collisions, the individual momenta of each of the balls can change, but the total momentum does not. It all came from that initial cue ball. So here's an example we'll take a brief look at during class. It's a little bit more complex than we need to worry about, but there are two pucks of equal mass. They have 100 grams collide on an air hockey table. Prior to the collision, puck 1 travels in a direction that can be considered in the positive x at 1 meter per second. So it's going to the right at 1 meter per second. And puck 2 travels in the negative y at 2 meters per second. And so these two come together and they hit perfectly. And then after the collision, puck 2 goes up and to the right. So what happens to puck 1? So it's pretty complex. But puck one is going to go down and to the left. But how much does it go? And we'll use the conservation of momentum in each dimension to figure that out. But other than that, that's your quick little introduction to momentum in two dimensions. There are a couple of homework problems that get into it. It's not a big deal, but it is a very important application. It's taken the next level step in solving actual collision problems.